So we have the coin and then we have this die. So when I flip a coin, what could the coin land on?
Heads or tails?
Yeah, heads or tails. So let's say the coin landed on heads. So we're gonna say the coin landed on heads. So then I'm gonna roll the die. Now, when I roll the die, it can land on 1, 2, 3, 4, 5, or 6. So one of the outcomes that could occur for my sample space is that when I flip the coin, it land on head, and then when I roll the die, it can land on 1. Other outcome that could occur is I get heads, and then it land on 2. Or it could be I toss a coin, I get heads again, and then the die roll a 3. Or I could get heads, oops, and the die land on 4. I could toss another head, and the die could land on 5. Or I could get head, and the die land on 6. So far I have those 6 outcomes. What are the other 6 outcomes that could occur?
Tails?
Cool. So it could be tail. So now it could be tail, and the die land on 1. Tail, the die land on 2. Tail, the die land on 3. Tail, die land on 4. Tail, 5. Tail, 6. So that will be your sample space. So in this sample space, how many total outcomes do I have?
12.
Perfect. So you have 12 total outcomes. All right, and that's it. Any question on that sample space? All right, so let's move on to the next problem. All right, so for this one said the probability experiment determines the number of outcome and identify the sample space. A probability experiment consists of recording a response to the survey statement at the bottom and the gender of the respondent. So should there be a limit to the number of terms a U.S. senator can serve? So they give them the option saying agree, disagree, or no opinion. So for this one, you kind of want to pay attention. So for this one, we want the respondent. So what did they respond? Did they say agree, disagree, or no opinion? But we also want their gender. So for this one of the sample space could be that the person is male. And the person is male and they agree with the statement. Or another outcome could be the person is male and they disagree with the statement. Other thing could be they're male and they have no opinion. Cool. So we already have all of the males. So now we want to do the female. So we could say they could be a female and they could agree with the statement. They could be a female and they disagree with the statement. Or they could be female and they have no opinion. And that's our sample space. So if you look at the sample space, it's listing all possible outcomes that could occur when we're recording their gender, but we're also recording the response to this question. So for this one, how many total outcomes do I have in my sample space? All right, so we'll go with 6 outcomes. All right, and that's it for that last problem. Any question for that last problem? All right. So let's do this last one. A probability experiment consists of recording a response to the survey statement at the left and the political party. Well, let's forget about the at left. So we just want to record the political party of the respondent. So all we care about is the political party. So pretty much our sample space would it be whether they're Democrat, Republican, or others. So those are all of the outcomes that could occur for our sample space. So they can either say they're Democrat, Republican, or they're other. And that's it for that last problem. Any question for this problem?
No.
So just remember for sample space, you're listing out all of the possible outcomes. All right, so up next we're again to the fundamental counting principle. So the fundamental counting principle, it should help us with the last questions because the fundamental counting principle is going to tell us how many total outcomes could occur. So for say, let's do a tough one. All right, say if we wanted to use the fundamental counting principle for this one. So the fundamental counting principle, you have to ask us to list out how many outcomes each event have. So say, I don't really want to draw this again. We'll copy this, paste it here. Perfect. So let's look at a coin. When I flip a coin, how many options do I have? Like, what can I land on?
Heads or tails?
Heads or tails. So that means we have 2 outcomes. But if you look at the die, how many outcomes does the die give us?
6.
Yeah, 6. So what the fundamental counting principle says, if I know how many outcomes each individual event give me, if I multiply them, they will give me the total outcome or the total amount in our sample space, which is 12. So we can also do that in the next one. So if you look at this one is gender. And we have, well, the response. So for gender, if you look at gender, there's only 2 options. They can either identify as a male or identify as a female. So we have 2 options. If you look at the response, they have 3 responses they could choose from, either agree, disagree, or no opinion. So if I do 2 times 3, we get 6. And if you look over here, that's how many total outcome we have. So that's how we're going to use the counting method. The counting method is the other way to kind of tell us like how many total outcomes should we have. All right, so let's go ahead and do a problem. All right, so for this one says you are purchasing a car, a new car. The possible manufacturer, car size, and color are listed. So for the manufacturer, you're either going to choose Ford, GM, or a Honda. For the car side, you're either going to choose a compact or a mid-size. So, and color, you can either choose white, red, black, or green. So for this one says, how many different ways can you select one manufacturer, one car size, and one color? Use the tree diagram to check your result. All right, so we'll use the tree diagram after this. All right, so first we're gonna do the counting method. So for the counting method, what you first wanna do, you wanna see what are all of the, what are all of the things that you could choose from. So if you look at it, I could choose the manufacturer. So we'll just say manufacturer. I could choose the car size, and we could choose the color of the car. So those are the 3 things that I can actually pick out for this car. So all you have to do is list out all of your options. So if you look for manufacturer, you go like, how many different options do I have to choose from? Well, I have 3 different options to choose from because we have Ford, GM, and Honda. So we have 3 options for the manufacturer. What about for car size? Well, for car size, if you look at it, you have 2 options. You have compact, sorry about that. You have compact and mid-size, so we have 2. Lastly, we have the color of the car. So we could choose white, red, black, or green. So you actually have 4 outcomes right here. All right, so far we got 3 manufacturer, 2 car size, and 4 colors. So all you want to do, multiply all of this. If you multiply them all out, what do you get?
24.
24.
Yeah, 24. So you say 24 outcome. All right, and that's all right. So if you want to double check your answer, you could always use a tree diagram. Let's see if I can. Wait. Like for a tree diagram, each branch is going to correspond to one of these options. So if you look at the first option you have the option to choose the manufacturer. So for the manufacturer, we have 3 options. So you do 3 branches. So we have 4. So I'll put F for 4, GM, I'll put G for GM, and I'll put H for Honda. So that's the first option you have. So once you choose which type of manufacturer you want, then you have 2 options on the side of the car. So we could either choose a compact car, or you could choose a mid-size car. So if I choose a 4, I have those 2 options. But if I choose a GM, I also have those 2 options to choose a compact or a mid-size. Also, if I choose a Honda, I still have those 2 options. So once you choose what type of size car you want, then what you could do, you could choose the color of your car. So if you look at it, we have 4 options. We have white, red, black, or green. So we could say white, red, black, or green. Let's do this one a little bit further out. So we can say white, red, black, and green. This one you can say white, red, black, or green. Let's do this one right here. White, red, black, or green. Yeah, white, red, black, or green. And lastly, we'll do white, red, black, run out of space over here, or green. So if you look at each one of these options, so each one of these branch, it's pretty much telling us the outcome. So if I look at this branch over here, so say if I look at these branch over here, that means I chose a GM car, it's compact, and it's white. Or if I wanted to, I could go this route. So I could pick a Honda, is mid-size, and is black. So if you look at the end of the black branches, each one of those represent one outcome. So here you go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24, which matches up with this. So we said we should have 24 outcome. All right, and that's it for that last problem. Any question for that one? All right, sweet.
I'm sorry.
All right. So now it says your choices now include a Toyota. So that means for manufacturer, instead of only having 3 cars, now we have 4 cars because we're adding that we could pick a Toyota. It's also saying we're adding that we could pick a large car. So now for size, instead of only having 2 options, now I have 3 options. And now it's saying for the color of the car, we could pick a tan or a gray car. So we're adding 2 options to the color of the car. So that means we have 6. So now once again, what we're gonna go ahead and do, we're just gonna go ahead and multiply these all out. And this is gonna tell us how many total outcomes do we have. So it gets to tell us like how many total options do we have to choose a car from. So we go 4 times 3 times 6. And you get 72 outcomes. So it's telling us we have 72 different outcomes that we could choose when we're choosing the manufacturer, a size, and the color of this car. All right, so let's go on to the next one. So up next, we're going to go over how to find these probabilities. So to find these probabilities, if you look at the probability, so E represents your event. So E just represents the event. So let's do an easy one. So let's say my event is coin land on tail. So I just want the coin to land on tail. So we're going to say probability of E is equal to, so let's look at the top portion. It says number of outcome in event E. So how many different ways can a coin land on tail if I'm flipping the coin once?
Wait, what was the question?
How many different ways can a coin land on tail?
1.
Perfect, 1. All right, so that's what this top portion is asking. It is saying how many outcomes does your event have? So the bottom one is saying how many total outcomes are in the sample space. So for this one, when we flip a coin, how many total options or how many total ways can the coin land on one side?
2.
2. Okay, it could either land on head or tail. So you get 50%. All right. So that's how that formula works. So the top is how many outcomes does your event have. In the bottom is the number of outcomes in the sample space. All right. So let's go ahead and do this one. All right, so it said you roll a 6-sided die, find the probability of each event. So we're gonna do probability of A, which is event A. We're gonna do probability of B, which is event B. And we're gonna say probability of C, which is event C. All right. So for rolling a 6-sided die, how many total outcomes do we have?
6.
Yeah, so we have 6. So all of these we're going to be dividing by 6. All right. So what about rolling a 3? How many different ways when I roll a single die can I get 3?
1.
Yeah, so it should be 1. So if you look at a die, if you roll it once, there's only one way to get 3 is if it lands on 3. All right, so that's it for probability of A. Well, let's actually do that. So if I do 1 divided by 6, you get 0.16, and then you put the bar on top of it because that number is constantly repeating. All right, what is the probability of rolling a 7?
Same as
0.
0. Because it's pretty much impossible to roll a 7 if you have a 6-sided die. because for a 6-sided die, it only go from 1 to 6. It doesn't go all the way up to 7. All right, so rolling a number less than 5. So if I want a number less than 5, how many different outcome will give me a number less than 5?
4.
Yeah,
4.
because that's a 1, 2, 3, or a 4. So there's 4 outcome. So if you do 4 divided by 6, you get 0.66, and a number constant repeat. All right, and that's it for that one. So if you look at this one, all you have to do, you look at how many total outcomes do you have for your event, and you divide it by the total outcome in the sample space. All right, so let's move on down. Let's see. How many people know about playing cards?
Yeah.
Sir.
All right, cool. 2 people. All right. So when you have a playing card or a standard deck of card, you kind of have to just know there's 52 total cards. So there's 52 total cards. Of the 52 total cards, you're gonna have 26 black cards. So I always put 26 black, and you have 26 red. So essentially, half of the deck are black, half of the deck are red. So once you have half of your deck are black, half of your deck are red, half of the black card are going to be called spades. The other half are going to be called clovers. So we'll say 13 clovers. And then you have 13 spades. Same thing for the red card. Half of the red card are not going to be considered diamonds. The other half are going to be considered hearts. So we have, oh, that's horrible. So we have 13 hearts, and you have 13 spades. Well, sorry, 13 diamonds. And lastly, so if you look at it, you have 13 cards. So for each suit, so for you have 13 clover, you have 13 spade. So those 13 cards consist of ace, a 2, a 3, a 4, a 5, 6, 7, 8, 9, 10, a jack, a queen, and a king. So each clover, each spade, each heart, and each diamond have an ace, a 2, all the way through king. All right, so hopefully you got that now. So let's do probability of A, probability of B, and let's do probability of C. All right, here, let's do an easy one. Let's do B. So for B, just selecting a diamond. How many total diamonds do I have?
18.
13.
13. And you divide that by 52. If you do 13 divided by 52, you actually get 0.25, which makes sense because since you have 4 suits, each one of them are equally balanced. So if you pick one suit out of the 4, you got a quarter of them. Okay. So let's do probability of A, selecting a 7 of diamond. So we want a card that's a 7 of diamond. How many cards do we have that are 7 of diamond?
1.
Yeah, so we have 1 out of the 52 because there's only 1 7 of diamond. So if we do 1 divided by 52, you roughly get 0.019 and so on and so forth. All right. Let's do probability of event C. So selecting a diamond, a heart, a club, or spade. So how many cards do we have that are diamond, heart, club, or spade? Oh, sorry. This is called a club. I just call it a clover.
Would this be 52?
Yeah. So you have 52 out of 52. You're essentially selecting all of the cards. So that's 100%. All right. And that's it for that last one. Any question in regards to that? All right. All right. So up next, we're going to have a definition. So the definition for this one is the law of large number. So the law of large number is saying that when we have a probability, the probability corresponds to the law of large number. Because whenever we have a probability, say like a flipping a coin, it doesn't mean it's always going to be 50%. Because if you flip the coin twice, it doesn't automatically mean one of them should be heads, one of them should be tails. The law of large numbers said if you do the event long enough, or if you do the event like for a good period of time, it should start getting closer and closer to 50%. So if you flip the coin like 1,000 times, it's saying based off of the law of large numbers, since you did that experiment long enough, it should be getting closer and closer to 50%. So the law of large numbers is saying the more you do the experiment, the closer and closer it should be getting to the theoretical probability. So that's what the law of large numbers says. So anytime you flip like a coin, like if you only flip it 5 times, it could be that all 5 times it can land on heads. And that's because the law of large numbers is saying you haven't flipped the coin long enough. But if you keep on flipping it, it should eventually start balancing out, and it should start getting closer and closer to that 50%. Right. Any question in regard to the law of large number? All right, so no. This is all right, so up next we're getting to something called a conditional probability. So a conditional probability is something that we kind of already know something has already occurred. So we want to find the probability of another event occurring. So usually this is the condition. So kind of like an example of that, say like if I already tell you it's already rainy, so we already know it's rainy, and then I ask you what is the probability that people will bring an umbrella? So we already know the fact that we already know the fact that it's already rainy. So the chances of somebody bringing an umbrella, it's gonna be higher, because if it's rainy, like it will be kind of silly not to bring an umbrella. But that's a conditional probability. But if I say, what is the probability that it's rainy and that somebody bring an umbrella, that's different, because in this case scenario, we don't know if it's already raining. So whenever we have a conditional probability, we already know a certain information about the event. So we already know that it's raining in this scenario I gave you. So the way that we find the probability, conditional probability, is this formula. So if you look at the symbol right here, this means and. So what we have to do, we have to find the probability of A and B. And then what we have to do is divide it by the probability of A. So if you look at it, you always divide it by the probability of the condition. So whatever the condition is, that's what you divide it by. So if I would have said probability of A given B, well, the top will stay the same. It will be probability of A and B. But for the bottom, you would divide that by the probability of B, because that's your condition. So you always divide it by the condition. All right. Any question for the formula before we move on and do an example? All right, let's go to this example. So for this one, it says 2 cards are selected in sequence from a standard deck. Find the probability that the second card is a queen given the first card is a king. Assume that the king is not replaced. All right. So for a conditional probability, there are certain words that tell you is a conditional probability. So for this one, the word that kind of tell me this is a conditional probability is the given that. As soon as you see given that, they're giving you the information. So they're giving you what has already occurred. So if you look at it, say given that the first card is a king. So what do I know about the first card?
It's a king.
It's a king. So we'll say the condition, the card is a king. And we want to find the probability that the second one is a queen. So for this one, I'm actually going to do it without the formula because it's actually easier to do it without the formula than to do it with the formula for this one. All right. So for this one, also, if you look at it, it says that assume that the king is not replaced. So what it means is once I select the first card, I'm not going to put it back into the deck of cards. So say if I select a card and we select the king and we select the king of spades. And we have all of these cards over here. So say we select the king of spades. How many cards are left?
51.
Yeah, so we have 51 cards. Oops. So we have 51 cards left. So that's what we divided by. So we divided by 51. So of those 51 cards, if the first card selected was a king of spades, how many of those 51 cards are considered to be queens?
4.
Yeah, 4. So you go 4 divided by 51. And you get 0.0784. And that's it for that one. So for this one, all you have to just understand, since we already know the first card was a king, that means we have one less card to choose from. Since we have one less card to choose from, you have to just account for that. So instead of dividing by 52, you divide by 51. And then the top card, or the top number, you just reflect how many queens are still in the deck of cards. So for this one, since me getting a king really doesn't affect the queens, I still have 4 queens left. All right. And that's it for that problem. Any questions for that last problem? All right. All right. So for this one, we're going to use the formula, but for this one, it's kind of also easier to not use a formula. But let's do the formula for that. You can kind of get used to the formula, and then I'll show you how to do it without the formula. So for this one, says the table showed the result of a study in which researcher examined a child IQ and the presence of a specific gene in the child. Find the probability that a child has a high IQ given the child has the gene. All right, so if you look at the table, so here go high IQ, here go normal IQ. Here go people who have the gene. Here go people who do not have the gene. So for this one, if you look at it, you have this key word over here. We have given. So what's the given?
That the child has a gene.
Perfect. So the given is the gene is present. All right. So what is it that we're trying to find? We're trying to find the probability that the child has a what?
A high IQ.
Oh, there you go. So say high IQ. All right. So for this one, what we have to do, we have to find the probability they have a high IQ and the gene. Oh, that did not turn out the way I wanted. And the gene is present. And then what you want to do, you want to divide this by the probability of the condition. So the condition is that the gene is present. So you divide it by the gene is present. So I'm just using the formula right now. Everybody good so far with the formula setup?
Yes, sir.
All right, so let's do the top. So for the top, what we want to do, we just want to get the probability that they have a high IQ and the gene is present. So kind of like the easy way to think about this, you're looking for where do they intersect. So what you want to do, you select high IQ. So here go high IQ. Here go gene is present. So where do they intercept? Well, they intercept at 33. So we put 33 divided by 102. So that's how you do the probability of high IQ and gene is present. You pretty much just see where do they overlap, because where do they overlap are the people who have a high IQ and that the gene is present. So we have 33 people who have this gene and have a high IQ. So up next, we're gonna go ahead and do this. So we're gonna do the probability the gene is present. So how many total people do we have that have this gene?
72.
Yeah, 72. And you divide this by 102. So up next, what you want to do, if you look at it, we have a complex fraction. Anything you want to get rid of a complex fraction, you multiply the bottom fraction by the reciprocal. So the reciprocal of this will be 102 divided by 72. So the 102 cancel, the 72 and the 72 cancel, but you multiply the top also. So the 102 cancel. So the only thing left is the 33 on top and the 72 on the bottom. So you get 33 divided by 72. If I do 33 divided by 72, and you get 0.458. And that's it for to use the formula. Any question on how I found the probability using the formula?
No.
All right. So up next, we're going to do it logically by just using the two-way table. So for this one, what is my condition? Well, the condition is that we know the gene is present. So if I already know the gene is present, then I just want to focus on these people over here. So if you look at how many total people do we have that have the gene? Well, there's 72. Now what you want to look in those 72 people, how many of them have a high IQ? Well, 33 of them have a high IQ. So you go 33 divided by 72, and you get exactly the same thing that we got over here, and you should get 0.458. So if you have a two-way table, it's actually easier just to look at the two-way table. Just look at the portion that's your condition. Since the condition in this case scenario is they do have the gene present, you just focus on people who have the gene present. All right, and that's it for that part. So let's do some more. So it's the same thing. So let's do one. So for one, it says find the probability that a child does not have the gene. So we want them not to have the gene. So how many people don't have the gene?
30.
Yeah, 30. And if you look at the sentence, they didn't say anything about given that. So we know it's not a conditional probability. So you just divide it by 102. So if I do 30 divided by 102, 30 divided by 102, you get 0.294. And you're all done with number one. So for this one, it was like, so it says not present. That's why I'm using this one. All right, so let's do 2. It says find the probability that a child does not have the gene given that the child has a normal IQ score. All right, so for this one, what's given to me? What does the child have?
A normal IQ.
Yeah, a normal IQ. So what we're gonna do now, we're only gonna focus on these child. So if you look at it, there's a total of 50 child that have a normal IQ. So are we looking for child who have the gene present, or are we looking for child who don't have the gene present?
Don't have
Without
the
the gene.
Don't have the gene. So if you look at it, you have 11 of them who don't have the gene. So if you do 11 divided by 50, that will actually give you 0.22. And that's your answer for that one. So you just kind of look at the difference. If they don't say anything like given that, then pretty much you know it's not conditional. But if you do see given, that means they're giving you the condition and it should be a conditional probability. So let's move on down. All right. So up next, we're going to go ahead and work on something called the multiplication rule. So the multiplication rule is meant to be like a shortcut way how to get a probability. So we have 2 multiplication rule, one for independent event and one for dependent event. So for this one, it's for dependent event. All right, so what I mean by dependent event just means that the probability of one event affect the probability of the other event occurring. So let's say the probability that is rainy will affect the probability of you bringing an umbrella because they're kind of dependent on each other. Because if it's already raining, you're more likely to bring an umbrella. But if it's not raining, you're less likely to bring an umbrella. So those are dependent events. So one event influences the probability of the other event. Independent event just means one event doesn't influence the other event from occurring. So say the event is rainy and the event that you get an A in your statistic exam. One event does not influence the other because if it's rainy, it doesn't make it more likely or less likely of you passing the statistic class because they're independent from each other. One doesn't influence the other. So if they're dependent event, if I want to find the probability of A and B, you get the probability of A and you multiply it by the probability of B given A. If the events are independent from each other, if I want to find the probability of A and B, you get the probability of A and you multiply to the probability of B. So pretty much at the end of the day, you're just multiplying these 2 probability in order to get probability of A and B. So let's go ahead and do some example of this. All right, so for this one, said 2 cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king and then selecting a queen. All right, so we want to find the probability. One of the card is a king and then selecting a queen. All right, so do the cards influence each other? And the answer for this one should be yes. The cards do influence each other because we're doing it without replacing. Because if we're replacing the first card, then it wouldn't influence each other because if I get a king the first time, then I could put back the king and now the probability would still be the same for the queen. But the thing is, since we're doing it without replacing the card, that's what makes this a dependent event because once I get my first card, it's going to influence the probability of the second card. So for this one, we're going to say the probability, the first card is a king. And we're going to multiply this by the probability the second card is a queen. given the first card was a king. Okay, if you look at it, we're going to say the first card we get, so we'll put right here, first card. We're going to say the first card is a king. And then when we're selecting our second card, we're going to say we want to find the probability the second card is a queen, given we already picked a king. So that's how you want to write it. So what's the probability the first card is a king?
4 out of 52.
Oh, 4 out of 52. Thank you. All right. So once again, we picked a king. So let's say we now pick a king. We picked the king of diamond. So we have our deck of cards. You have some sort of design on it. So now when I'm picking the queen, how many cards do I have to choose from?
51.
Yeah, 51, good. But how many queens do I have in those 51 cards?
4.
Yeah, you still have 4. So then what you want to do, you want to do that in your calculator. Here, let me do this with the class cal, so that way you can see how to enter it, in case you're wondering how to enter. All right, so in class calc, if you want to do this, well, let me get the keyboard. There you go, keyboard. So you could just do 4 divided by 52. Oops. Let me get some of this out of the way. And then if you look at it, I want to use the right arrow. You have to get in front, and then you say multiply by 4 divided by 51. And if you look at it, we get 0.006. So it's not very likely for me for the first card I get is a king, and then the second card that I get is a queen. And that's it for that first problem. Any question for that first problem? All right, so let's do the second problem. So for the second problem, it said a coin is tossed and a die is rolled. Find the probability of getting a head and then rolling a 6. All right, so we have a coin. Here, let me try doing the face again. Look better, not that much. All right, so we toss a coin and then we roll a die. So if a coin land on heads, does that make it more likely that when we roll a die, it's gonna land on 6?
No.
No. So these events are independent from each other. Because one event doesn't influence the other event because they're independent from each other. So what we want to do, we want to find the probability when we toss a coin, it landed on heads. And then when we roll a die, it land on the number 6. So we want to find the probability it land on heads. And then we multiply that by the probability it will land on 6. So what's the probability that the coin will land on heads? So when I flip it, what's the probability it will land on heads?
50%.
Yeah, 50%. Or in this case, I'm going to say 1/2, just for that we could keep as a fraction. What about for the die? What's the probability that the die will land on 6?
1/6.
Yeah, 1/6. So then we could do 1 divided by 12. And if we do 1 divided by 12, you get 0.083. And technically the 3 repeating, so you want to put a bar, but you don't really have to. And that's it for that probability. So can you guys know the difference between independent event, which this one was, and this one, which was dependent? Any follow-up question for this problem? All right, so let's do this one. A coin is tossed and the die is rolled. Find the probability of getting a tail and then rolling a 2. So you want to find the probability of getting tail and then getting a 2. So if you look at this one, these are independent events again. So we want to find the probability of getting tail and then probability of getting a 2. So if you look at probability of getting a tail, well, it's the exact same probability of getting heads is 1 out of 2. So the probability of it landing on 2, well, it's the exact same probability of it landing on 6. So it'll be 1 out of 6, which is 1 out of 12, which 1 out of 12 is equal to 0.083. And that's it for that last problem. Any question for that last problem? All right, so let's use the multiplication rule to find these probability. So 2 cards are selected from a standard deck, a deck without replacement. Find the probability that they are both hard. So for this one, if you look at it, it says without replacement. So that's telling me these are dependent. So let's do A right here. So we want to find the probability both of them are hearts. So we want to find the probability that the first card we get is a heart and the second one that we get is a heart. So since this is dependent, we're going to first find the probability the first card is a heart. And then we're going to multiply it by the probability that the second card is a heart. But given the first card has to be a heart. So what's the probability that this first card is a heart? How many total hearts do we have?
13 out of 52.
Perfect, thank you. So we have 13 out of 52. So for this second one over here, it's saying what's the probability the second card is a heart given that the first one was a heart? So let's just say theoretically that the card I chose was the ace of heart. So I chose the ace of heart. So if I chose the ace of heart, how many hearts are left?
12.
12, perfect. And then this will be out of 51. So we'll say 13 divided by 52 times 12 divided by 51. If you do that multiplication, you should get 0.0588. All right, and that's it for part A. Any question in regards to part A? All right. Let's do part B. So for this one, so the probability that a particular knee surgery is successful is 0.85. Find the probability that 3 knee surgery are successful. So this one is a little bit different because for this one, instead of only having 2 events, we actually had 3 events. Because we want the first one to be successful. We also want the second knee surgery to be successful. And we want the third one to be successful. So what we have to kind of figure out is this dependent or this independent. So if one knee surgery is successful, does that change the probability for the second person who's getting the knee surgery? That, like, does that change the probability, make it higher or smaller? Or it is still pretty much will just be 85%?
It would still be 85%.
Yeah, so it'll still be 85%. So that means they're independent. Because if the probability doesn't change it, that means it's going to be independent. If the probability does change, it's dependent. So to find this, we're going to find the probability the first one was successful, second one was successful, and the third one was successful. So you get probability of success, multiply it by probability of success, multiply by probability of success. So we say 0.85 times 0.85 times 0.85. But if you know math, and you know there's a shortcut way of how to do this. Because they're saying 0.85 times 0.85 times 0.85. All you have to do is see how many times does 0.85 occur. So 0.85 occurred 3 times. So we do that 0.85 to the third power because we're doing 0.85 times 0.85 times 0.85 3 times. So let me show you how to do this with the TI, well, not the TI, sorry, with ClassCalc. All right, so for ClassCalc, you do 0.85. And what you have to do, here, let me get my annotation thing. Let's do spotlight. Cool. If you look right here, it says a to the second power, but I don't want a to the second power because we don't want to do it to the second power. You want to choose a to the n power. And then if you look at it, it lets you select which power to do it from. So I'm going to say to the third power. So if you look at it, you get 0.614. 0.614. Cool. And that's your answer. And that's how you do exponents in the ClassCalc. All you have to do is put a to the n power, and then you can put any variable or any number for that power. Yeah. So let's go ahead and transfer back. So if you look right here, I put that answer 0.614. So let's do C. So if you look at C, it says the probability that none of the 3 surgery is successful. So we want all of them not to have a good surgery. So we want the first one to fail, we want the second one to fail, and then we want the third one to fail. So we want all 3 of them to fail. So right here, we're gonna say probably the first one fail, and the second one fail, and the third one fail. So if I know the probability that the knee surgery is successful at 0.85, how can I find the probability that the knee surgery is not successful?
You subtract it by 100.
Yeah, so you do 1 minus 0.85. If you do 1 minus 0.85, here I'll put it right here, probability of failure is equal to 1 minus 0.85, which is equal to 0.15. Because they're pretty much complementary event. Cause it's either gonna be successful or it's gonna be a failure. There's kind of no in between. So for this one, we're gonna say 0.15 times 0.15 times 0.15. So let me do that in my calculator. So if I do 0.15 to the third power, you get 0.0034. And that's it for that one. So just remember, like, they're complementary events because it's either going to be a success or it's going to be a failure, but they're kind of like no in between. All right, everybody go for C.
Yeah.
All right, so we're going to skip D, so don't worry about D. All right, so let's do this next one. So it says in a jury selection pool, 65% of people are female. Of these 65, one out of four work in the health field. So for part A, it says find the probability that a randomly selected person from the jury pool is female and work in the health field. So we want to find the probability they are female and they work in the health field. All right. So for this one, what percentage are female?
Like 65.
65?
Yeah, 0.65. So if you look at it, it says of these 65%, one out of four work in the health field. So they're giving us a conditional because it's telling us we already know they're female. And of these 65% female, we know one out of four work in the health field. So when we want to find, well, what percentage of people work in the health field? Well, not people, how many female work in the health field? You would say one out of four, or you could say 0.25. So if we do 0.65 times 1 out of 4, 0.65 times 1 out of 4, we get 0.1625. Right. And that would be it for A. Any question in regard to A? All right, so let's do B. Let me put this for A, this for B. So if you look at B, it says find the probability that a randomly selected person from the jury pool is female and does not work in the health field. So we want them to be female, but we don't want them to work in the health field. So the probability of them being female is still going to be 0.65. But now, instead of us wanting them to work in the health field, now we want them not to work in the health field. So if I know 1 out of 4 work in the health field, how many of them don't work in the health field?
3 out of 4?
Yeah, 3 out of 4. So what you want to do, you want to do 0.65 times 3 out of 4, 0.65 times 3 divided by 4. And for this one, you should get 0.4875. All right. And that'll be it for that problem. So for this one, you do kind of want to know like how to use a complement rule because it will help you out. Because like for this one, if we already know the probability of them working in the health field is 1 out of 4, the probability that they don't work in the health field, well, you have to do the complement of that. So you have to do 1 minus 1 out of 4 and you get 3 out of 4, or you could just get 0.75. All right, but that's it for that one. Any question in regards to the last problem? All right, so let's do mutually exclusive. So when we talk about two events could be mutually exclusive because two of those events cannot occur at the same time. So mutually exclusive just means either one event is going to happen or the other event is going to happen, but both events cannot occur at the same time. So let's kind of go back to the last problem. So the event could be a person is female or a person is male, but they can both be a female and a male. It's mutually exclusive because you either identify as one or you identify as the other. Or also look at the last problem. You either work in the health field or you don't work in the health field. Those are mutually exclusive because either you work in the health field or you don't work in the health field, but you can't have both of them. All right. So let's go down and let's do some example. So if you look right here, I have two events. So all we want to do is say if they're mutually exclusive or they're not mutually exclusive. So we have A, which said event A, roll a 3 on a die, or event B, roll a 4 on a die. So are these two mutually exclusive or are they not mutually exclusive?
They are mutually exclusive.
Yeah, so we'll say ME. So we'll say they are mutually exclusive because if I roll a die, you can roll a 3 and a 4 at the same time. It either gonna land on 3, it either gonna land on 4, or it'll land at some other number. But it's pretty much impossible if I roll a die for it to roll on 4 at the same time. All right, and that's it for A. Let's do B. So for B, so event A is randomly select a male student. Event B, randomly select a nursing major. So are these two events mutually exclusive from each other, or can they occur at the same time? Because can I have a male student who's a nursing major? Like, is that
Yeah.
possible?
Yes.
Yeah. So for this one, you want to say not mutually exclusive. Because since both of those events could occur at the same time, we say they are not mutually exclusive. All right, let's just see. It said event A, randomly select a blood donor with type O blood. Event B, randomly select a female blood donor. So are these two events mutually exclusive, or is it possible for a female blood donor to have type O blood?
Yeah, it's not again.
Yeah, so it is possible. So we'll say not mutually exclusive. All right, and that's it for that one. Any question in regard to that last row? All right, so let's scroll on down. Go. All right, so what I want you to do, I want you to do these example. So you just look through them, you say, are they mutually exclusive or are they not mutually exclusive? So what I want you to do, I'm gonna do a poll and I want you to tell me whether A, B, or C are mutually exclusive. So you tell me either A mutually exclusive, B mutually exclusive, or C mutually exclusive. Or if all of them are mutually exclusive, you put D. Actually, that's confusing. Well, just do them, and on the chat, you tell me which of them are mutually exclusive. So if A and C are mutually exclusive, on the chat, you type in A and C. So just work on those right now. Cool. All right, so we have one person to answer. Cool. Good job, Caesar. All right, so let's go over this. So for part A, it said, event A, randomly select a 20-year-old student. Event B, randomly select a student with blue eye. So if you look at that, those are not mutually exclusive because I could pick a student who's 20 years old and they can have blue eyes. So this is not mutually exclusive. All right, part B. It says event A, randomly select a vehicle that is a 4. Part B, or event B, randomly select a vehicle that is a Toyota. So for this one, we'll say not mutually exclusive. Well, sorry, we'll say mutually exclusive because it's not possible for me to choose a 4/Toyota car. You either get to select the 4 or you're going to select the Toyota, but it's not possible for you to select a car that's a 4 and a Toyota. So for this one, should be mutually exclusive. Lastly, randomly select a jack from a standard deck of car. Randomly select a face car from a standard deck of car. So for this one, you do kind of have to know a face car is a jack, queen, and a king. So since a jack and a face car, so technically they're not mutually exclusive. Because when I say a face car, I could still select a jack. So for this one, would not be mutually exclusive. All right. And that's it for A, B, and C. Any question in regard to A, B, or C? All right. So let's go over this. So for this one, we're going to go over the OR statement. So the OR statement is called the addition rule. So for the addition rule, anytime you see this symbol over here, this represents OR. So this is saying find the probability that A or B occur. So it doesn't matter if only A or B is happening. We just care if either A or B is occurring. So if the events are not mutually exclusive, we're going to do probability of A plus probability of B minus probability of A and B. So that's if it's not mutually exclusive. If it is mutually exclusive, all you have to do is find the probability of A and add it to the probability of B. Any question in regard to those formulas so far? All right. All right, so let's do this first problem. So it says you select a car from a standard deck. Find the probability that the car is a 4 or a ace. So right here, that's the key word, or. If it always says and, you could do that. But since it says or, you want to do this where it says probability of 4 or a ace. So first thing you want to do is decide, is this mutually exclusive or is this not mutually exclusive? So for this one, is it possible if I'm selecting one car for that one car to be a 4 and an ace at the same time? Well, the answer should be no, it's not possible. So for these events, they're mutually exclusive. So since they're mutually exclusive, what we're going to do, we're going to find the probability we get a 4, and we're going to add it to the probability we get an ace. So what's the probability that if I randomly select a car, the car will be a 4?
Four out of 52.
Oh, good. 4 out of 52. So then we want to add it to the probability of getting an ace. So for the ace, it'll be the same thing because there's 4 aces. So you go 4 divided by 52. So if I do 4 divided by 52 plus 4 divided by 52, since they have the same common denominator, you can just say 8 divided by 52. So if I do 8 divided by 52, you will get 0.1534. All right. And that will be your final answer for A. So A, our final answer will be 0.1534. All right, let's do B. So for B, say you roll a die, find the probability of rolling a number less than 2 or rolling a odd number. So we want to roll a number less than 3. So less than 3 or an odd number. All right, so first thing you want to see are these mutually exclusive. So mutually exclusive mean either one occur or the other occur, but both of them cannot occur at the same time. So is it possible if I roll a die that the die could give me a number that's less than 3, but also is an odd number?
Yes.
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 So what we're gonna do, we have to find the probability is less than 3. Added to the probability is an odd number. So I'm gonna put odd. And then subtracted by the probability is less than 3 and odd. All right, so let's do this one first. How many number in a die, sorry about that. How many number in a die are less than 3?
2.
Yeah, so you put 2 out of 6. Plus, how many odd numbers do we have in a die?
1.
Let's try that again.
3.
3, there you go. Because remember, odd will be 1, 3, and 5. So how many numbers do we have that are less than 3 and are odd number?
1.
Yeah, 1, which is 1. So we get 2 out of 6 because that's how many numbers we have that are less than 3. We have 3 out of 6 because that's how many odd number we have. And then we subtract it by however many number we have that are less than 3 and are odd. So if I do this, you get 2 over 6 plus 3 over 6, which is 5 out of 6. And then if you do minus 1 out of 6, you get 4 out of 6, which is 0.66. And it's repeating. All right. And that's it for that last one. Any question for that last one? Yeah, so we're gonna do one more and then we'll just stop and then we'll continue this tomorrow because this one is a pretty long lecture. All right, so for part A, it says a die is rolled, find the probability of rolling a 6 or an odd number. So we want a 6 or a odd number. So are these two events mutually exclusive? Can they occur at the same time? Can I get an odd number that's a 6?
No.
No. It's either going to be a 6 or it's going to be an odd number, but it's not possible for both of them to occur at the same time. So for this one, you have to do probably a 6 and add it to the probability of it being an odd number. So what's the probability of me getting a 6?
1 over 6.
Yeah, 1 over 6. What's the probability of getting an odd number? Well, we already found in the last one is 3 out of 6. So if I do 1 out of 6 plus 3 out of 6, you get 4 out of 6, which is 0.66, and you just constantly keep on going. All right, and that's it for A. Any questions for A? Let's do B. So for B, it says a card is selected from a standard deck. Find the probability the card is a face card or a heart. So we want to get a face or a heart. So is it possible that one of the face cards could have a heart?
Yes.
Yeah, so it is possible. So for this one, we have to do probability of a face card plus the probability of a heart minus the probability of a face and a heart. So remember, a face card is a jack, a queen, and a king. So, and if you remember, each one of them have 4. So how many total face cards do we have?
12?
Yeah, 12 out of 52. How many total hearts do we have?
13.
There you go. Minus. So now we want pretty much how many face cards have a heart. So if you look at the jack, there's only one jack that has a heart. If you look at the queen, same thing. If you look at the king, same thing. There's only one of each that have a heart. So how many total face cards have a heart?
3 over 52?
Yeah, 3 over 52. So if you do that, you should get 22 over 52. So then if you do 22 over 52, you get 0.423. So you get 0.423, and that's it for that one. Yeah. Any question in regard to that last one? All right, so let me show you where the homework gonna be, and technically you can get started with the homework because this is like the only new thing I want to do, but you do kind of want to just go over some of it. So let me show you where the homework is gonna be, where the activity is gonna be. Cool. And also where the test is gonna be. Well, sorry, not the test, the quiz. All right, so for the homework we're still gonna be over here. So we're in this new one. So we're in chapter 3 probability topic. So you click over here and you want to click on this first one. So technically we did this first one. You could technically get started with this one. Like I just need like 2 more problems, but you should be able to do it. So you could get started with probability. You could also get started with the activity. So for the activity, you click over here. I think we're in activity number 9. Let's make sure. Oh no, we're definitely not activity number 9. But you want to go right here, activity 10 and 11 for chapter 3. So you go right here, and you're going to be able to do activity number 10. So you start working on it. Like I gave you pretty much all of the formula that you need to be able to do this. So let's go ahead and start doing this one. So that's the activity, and also for today's quiz. So you should be over here. And I think you should be under quiz number 8. Yeah. So you want to do quiz number 8, and for that one you're getting 40 minutes. So that should be enough time for you to be able to do the quiz and also submit the quiz to me. I still haven't graded all of yesterday's quiz. I should be able to do that in a little bit. So by the end of today, you should be able to see your grade. Also, for some of the homework problem, if you feel like some of the homework problem I didn't go over, what you could do, just email me when it says email instructor in the bottom. And if I feel like I didn't give you enough information, I'll just take away that problem from your homework set. So if you ever feel like one of the homework problems is too much, or something like that I didn't go over, just email me. I'll look at it and I'll see if I gave you enough information to do that. If I feel like I didn't, I'll take it out for that way you don't have to worry about it. All right. Cool. Any questions before I close out this meeting?
What is quiz 8 on?
It's gonna be on yesterday. So if you remember yesterday was essentially just like a review. So it's gonna be on linear regression. It's gonna be like on correlation coefficient, so stuff like that.
All
Are
right.
we having office hours today?
Yeah, I'm gonna have office hour. Like as soon as I close this down, I'm gonna go to my office hour, and that way, if you have any question, you can just jump into my office hour.
So all quizzes from now on are going to be from the previous day, the previous lesson?
Yeah, they've always been like that.
Oh.
Yeah. Yeah, the quizzes are always from what we learned the previous day.
Have you graded the activities yet?
Now, for the activity, I'm gonna grade them all the way to the end because the thing is, like some students either train the same day or some students just wait until like the last minute to do it. So it'll just easier for me to do and just grade them the day they're due because that's way I know everybody have at least turned it in or turned it in before the due deadline. So I haven't graded any of the quizzes. Any other questions? All right, cool. So I'm gonna close out this meeting. I'm gonna go to my office hour. So if you do have any further questions, jump into the office hour. All right, guys, later.